Hello, welcome to another video. Today we're going to be talking about what's known as implicit differentiation, which is just this idea where we're solving for what's known as dy over dx, or the derivative of y with respect to the derivative of x. So before, when we referred to derivatives, we were using stuff like f prime of x, or the d over dx, which is the derivative with respect to the derivative of x. And all we're doing here is we're saying the derivative of y with respect to the derivative of x. And the reason we're trying to solve for this is because we're going to have some sort of expression like x plus y equals to some number, and we're going to try to find this dy dx by taking the derivative of every single variable, not just the x. So that's all really we're doing. Once you get used to having this dy dx in the equation, everything else feels pretty standard. So let's try an example, and it'll make a lot more sense once you see it. So let's say you had something like 2x plus y squared equals to, let's just say, 10, for example. So how would we do this? Well, let's just take the derivative of everything. The best way to kind of think about this in your head is to treat every single variable kind of like how you would with an x, and then just add this dy dx for any time you take a derivative of a y. So for example, let's just start with the x. So we know the derivative of x is 1. 1 times 2 is 2. For the y, let's just treat it like an x, so bring the 2 down for the power rule, then decrease it by 1, so we get 2y, and remember we just want to have this dy dx, so we just multiply it by dy dx, kind of like an additional component. Then we have this 10. Remember that 10 is a constant, so just like any other time, it's a 0. Now, it's going to ask you to solve for dy dx, so we kind of just treat dy dx like it's a variable, and we want to solve for it. So we would subtract 2, and then we would have 2y dy over dx equals to negative 2. Then we would just divide by 2y, because we're trying to get this dy dx by itself. So we want to then divide this side by 2y as well. Then we do have this dy dx equaling some value, and it's going to be dy dx equals to this, but remember we can't actually cancel these 2's, so that means we have negative 1 over y, and this right here would be the answer. So you are going to usually get some variable, usually many different x's and y's on one side. So just know won't be a number, but that's okay. It doesn't have to be just one single number. So let's try something similar. So let's say we had something like x squared plus maybe 3y squared minus a 2y equaling to, let's say, 21. So very similar. Let's approach the problem just like how we did up here. So first let's tackle this x1. So x squared, we bring the 2 down, we decrease the power by 1, so that turns into 2x. Then this 3y squared, we know that we bring the 2 down, so 3 by 2 is 6. And then we want to decrease the y's power by 1, so that's just 1. So it turns into 6y. Remember, we need that dy dx though attached to it. Then we want to take the derivative of this one right here. So we know that derivative of y is just 1, so this turns out to just be negative 2, and then dy dx. So we have two dy dx terms, but it doesn't matter. We can have as many as we want. Don't worry, it doesn't really change the process. So 21 though, remember it's a constant, so it turns into 0. Then what we want to do is, in this case, we first want, when we have more than one dy dx, we want to first get rid of all the terms that don't have a dy dx multiplied by them. So basically any term that's not a y, and we want to subtract or add them, whatever we need to do. So in this case, we're going to subtract this 2x, and we'll just rewrite everything else. Now, when you get really good at this, you can kind of do more than one step at once, but I personally would stay clear of doing that too much, only because at times that can create mistakes. So let's put the negative 2x over here, because remember we're subtracting 2x as well. Now what do we do here? Well, we want to factor out a dy dx from this. So we would factor out a dy dx. So this would be a 6y that's left over. This would be a 2, and we would still have this negative 2x on the end. Then we just want to divide by this, since we've taken out the dy dx, what we're trying to solve for. So 6y minus 2. So this cancels. Then we want to divide again by 6y minus 2. And what we do get is that dy dx is equal to negative 2x over 6y minus 2. So as you can see, not too bad of a process once you know how to do it. So remember, the key is usually we'll have to subtract or add things to get the dy dx alone, factor out a dy dx, divide or multiply, and then you'll have this usually big expression on the other side, which gives you the derivative of y, or this dy dx. So let's do something very similar to this, but let's try to use other things we've been taught. So we've kind of been using our standard power rules stuff, but what if we had something else? What if it was something like, let's just say 3x plus, let's just say 4x squared, and then we had a y that was attached to the x this time, and then that's equal to, let's just say 8. Okay, what would we do here? Well, let's start with the x, because we know very easily we can solve this derivative pretty quickly. So x's derivative is 1, so this is just 3. Okay, so if you notice though, this is a product rule. We have two variables, or two functions, multiplied by one another. We have this 4x squared, and we have this y. So whenever you see that, we're just going to use the product rule with the x and the y. So what I like doing is we're going to keep the plus here, then we're going to just make it very clear that this is a product rule we're doing in here. Because if there was a minus, we would want to kind of distribute everything after. So let's follow the rule. So the product rule states we have to take the derivative of the first one. So 4x squared's derivative, we would bring the 2 down. 2 times 4 is 8, so 8. And then that would be x, and since we subtracted by 1, we'd have just x to the first power. Then we would multiply that by just the second one, so y. And keep in mind, we have a y here, but we didn't take the derivative of y, so we don't have to put dy dx. So just keep that in mind. When you don't take the derivative of it, we're just carrying it over. You don't have to worry about putting that dy dx. Now, here though, when we take the derivative of the second function, y, we know that's 1, but we took the derivative of y, so we have to put the dy dx attached to this 1, because that's attached to a y derivative. And then we just kind of put the x1 right here. So 4x squared, we're just carrying over the second function. So this was just a product rule, we're just using x and y's instead. Okay, so that's that whole thing we did the product rule for. And then we equal that to this 8. And remember, it's a constant, so it's still going to be 0. Okay, so now let's distribute this plus. In this case, it doesn't matter too much, but we do want to be in the habit. In case it was a minus, it would matter. So 8xy plus, and since it's just a 1, we can kind of put this as just dy dx. But remember, it's still being multiplied by this 4x squared as well, and that's still 0. So now let's solve for dy dx. So remember what we wanted to do. We want to get rid of everything, put it on this side here that doesn't have a dy dx attached. So that would be this 3. So we're going to minus 3, and we're also going to minus 8xy because that doesn't have a dy dx. Now we're just left with 4x squared dy dx, and I'm just going to put the 4x squared in front just so it's clear it's part of the dy dx. And we're going to have this negative 3, and then we're also going to have this 8xy on this side. So again, it was just from here, we just moved it over. We subtracted it to this side. Okay, we're almost there. We just have to divide by this 4x squared because this is the problem. It's attached to the dy dx. Then we're going to divide by 4x squared on this side, and finally we'll get that dy dx equals to negative 3 minus 8xy over 4x squared. So like I said, you will usually just get a bunch of terms on one side. That is perfectly fine. All that matters is that everything is correct in terms of like moving things over. Okay, so I'm going to erase, and then we're going to come back and do some more examples. So let's say we had another example, and we were working on exponentials and the product rule as well, because we've kind of been increasing the difficulty slowly and introducing new things, but the process remains the same. So if we had something like e to the xy, let's just say, plus y squared, And let's mix it up and have something else on this side. And let's just say it was x plus 2, something like that. So besides from this e to the xy, everything is pretty similar to what you've already been doing. So let's handle this one first, and let's see what we have to do. So if you recall, the rule for the exponential for e's, for derivatives, is just going to be e to the u, so rewriting whatever is there, and multiplying it by u prime, so the derivative of whatever the top stuff is. So let's do that and see what happens. So we're first going to have e to the xy, and then we're just going to multiply that by the derivative of this top part. But as you can tell, xy is actually a product, so for u prime we actually will have to use the product rule. So let's do that though. So that would be the first function's derivative, so x, so that would be just really 1. And just because I think it would make it much more clear for this product rule especially, we're going to end up using a bracket here just so you can see what's going on. So x's derivative is 1, and then we'll just carry over the y, the second derivative. And because, remember, we didn't take the derivative of y, we don't have to put dy dx. Then we're going to add the derivative of the second function, so that would be 1 as well for y, but then it's going to be a dy over dx because this is still a y. And then we just carry over the first function, so x. And then this whole thing is for that xy derivative part. And then we can just do everything else. So we've done the e to the xy, now let's carry over to this y squared. So as we've already kind of been doing, we just bring down the 2 and then decrease it by 1, so that's 2y, but then it's also dy dx, because we did indeed take the derivative of a y. Then we're going to equal that to the derivative of x, so that would just be 1, and then of course that's a constant, so the 2 just turns into a 0. Now we just have to simplify a bit and do a few other things, but it's going to look kind of like we've already been working with the ones in the past. So this would be e to the xy, and 1 times y is just going to be y. And of course we're just going to add this dy dx and x, and since this is a 1, we can kind of drop it, so it just becomes x dy dx. So we're just moving things around, same exact thing. Okay. Then we're going to rewrite everything else. So this would be a 2y, and of course the dy dx remains. And then we still have this 1 over here. We can drop the 0. Now we're going to do something that seems intuitive, but it may not with all this stuff going on. We're just going to distribute this e to the xy to everything in the expression. So e to the xy times y is just going to be y multiplied by e to the xy, and then e to the xy times this x dy dx is just going to be x. Remember, we do want to keep whatever sign we had here, so x and then e to the xy, so the same thing, but then we're just going to add on this dy dx because we're still multiplying it by this x. And then of course we still have this 2y over dy over dx, and this is still equal to the 1. Now we just have to do what we've already kind of been doing. So we already know that when we have a bunch of dy dx's, we subtract whatever doesn't have a dy dx. And the only thing that doesn't have that is this one right here. So we're going to subtract by y e to the xy, and we're going to do the same thing here. So subtract by y e to the xy. Then we're just going to rewrite everything else here with the dy dx. That is an x to the e to the xy dy dx plus 2y dy dx, and of course we just have this 1 minus the y times e to the xy. So really just moving things around just like before. And just like before too, we're just going to take out all the terms that have this dy dx left. So that would be, if we take out the dy dx, we would have an x multiplied by e to the xy plus just a 2y, and that's going to be again equal to this 1 minus y to the e to the xy. And then just like before, we're going to divide by everything that we just took the dy dx out of to get it alone. So you're finding that even though the work involves more rules and it's a little more convoluted, it's the same exact process. We have more things kind of floating around almost. So we have a 2y here. We're just dividing by everything that was already here. So of course this cancels. So we just get the dy dx is equal to 1 minus y to the e xy all over x e to the xy plus 2y. So even though the actual process is longer, we had to use quite a few rules and move things around, the process is very similar. So just doing harder ones like this can guarantee you have the process down. So I'm going to come right back. We're going to do another kind of problem. Okay, so let's say we had another expression. So we've dealt a lot with power rules, we've done a lot of product, even exponentials. Let's try maybe some trig, utilizing trig with the chain rule, and let's see if we can do that just the same. So let's say we had something like the tangent of y squared, and this was minus 4x, and that's all equal to a constant 8. So what would we do here? Well, it turns out, even though it's essentially like a trig and different things, we can use essentially the same thing. So if you had an x here, so tangent of x squared, what would you do? Well, we would use the chain rule, and we would start with the outermost function. So the outer function here is tangent, so we would say this is going to be equal to the secant squared of just this y squared. And again, we didn't take the derivative of the inside, so we don't have to worry about using a dy dx here. And then we're going to multiply that by the derivative of the inside. And of course, y squared's derivative is 2y if we bring down the 2 and decrease it by 1. So this is multiplied by just a 2y. And of course, now that we took the derivative of the actual y, now we put the dy dx. Now we finished this tangent one right here. Now we just worry about this 4x. Of course, the derivative of x is 1, so it just becomes negative 4. And a constant is 0. Okay, now we just have to kind of solve for this dy dx. So of course we're going to add 4 to both sides. So this becomes the secant squared of y squared multiplied by 2y dy dx is equal to 4. And it might seem interesting here, like what should we do? Because usually we have either just one term of a dy dx and we divide that, or we have multiple dy dx's, we factor, and then we divide everything to the other side. But here we have multiple terms with one dy dx. What do we do? Well, it turns out actually the easiest thing to do here, when you have multiple terms by dy dx, we would do the most intuitive thing. We're actually just going to divide by everything in front of this dy dx, or multiplied by it. So that would be the secant squared of y squared multiplied by 2y. So then we would cancel that out here, and we would write that out, the secant squared of y squared multiplied by 2y. And then, following that, we would just have to put this as a dy dx is equal to 4 over secant squared of y squared multiplied by 2y. And if you wanted to, you could, of course, simplify this a little bit if your teacher wants you to simplify the terms and some trig. Sometimes they don't really. It doesn't matter to them if it's not in its completely simplified form. You just have to ask them.